The universe is full of mysteries. We look up at the stars and wonder about our place in the cosmos. But some of the biggest mysteries are not out there in the vastness of space. They are right here, hidden in the impossibly small world of atoms and particles. This is the quantum realm. It's a place where the rules of our everyday world don't seem to apply. And it's here that we find the key to a new kind of computing power. This is the world of quantum computing. It promises to unlock solutions to problems we once thought were impossible to solve. Let's begin our journey into this strange and wonderful dimension of reality. Your phone, your laptop, the computer that sent you this very message. They all speak a simple language. It's a language of bits. A bit is like a light switch. It can either be on or it can be off. We represent this with a 1 for on and a 0 for off. Every photo you take, every song you listen to is just a very, very long sequence of these ones and zeros. It's a powerful system. This binary code has built our entire digital world. For decades, this has been the foundation of all computation, a reliable and straightforward way to process information and command machines. But what if we could have something more? What if a switch could be both on and off at the same time? This sounds like something out of science fiction, but it's the reality of the quantum world. This is where the qubit comes in. The word qubit is short for quantum bit. It is the fundamental building block of a quantum computer. Unlike the classical bit that is stuck in one state or another, a qubit can exist in a combination of states. It holds more information, more possibility. It's not just a switch, it's a dial that can point to 0, 1 or anywhere in between simultaneously. This fundamental difference is what makes quantum computers so incredibly powerful. Imagine trying to find your way through a giant maze. A classical computer would try one path, hit a dead end, go back, and try another. It would have to check every single path one by one. A quantum computer using qubits can explore all the possible paths at the same time. This ability to exist in multiple states at once allows it to perform a huge number of calculations simultaneously. It's a cosmic leap forward in our ability to process information, opening doors to a new era of discovery. So, how can something be in two states at once? Let's explore one of the core principles of quantum mechanics: superposition. Think of a regular coin. When you flip it, it lands as either heads or tails. It can't be both. Now, imagine a magic coin. While it's spinning in the air, it's not heads and it's not tails. It's in a state of potential, a blur of both possibilities. Only when it lands, when you look at it, does it choose a side. This spinning, undecided state is like a qubit in superposition. It holds the potential for both 0 and 1 at the very same time. This isn't just a clever analogy, it's how things work at the subatomic level. An electron, for example, has a property called spin. We can measure its spin as either up or down. But until we measure it, the electron exists in a superposition of both spin up and spin down. The act of observing it forces it to choose a state. This bizarre behavior is not a flaw or a trick, it is a fundamental feature of our universe. Qubits harness this very principle. By keeping them in this delicate state of superposition, quantum computers can process a vast amount of information. The power of this concept grows exponentially. If you have one qubit, it can represent two states, 0 and 1, at once. If you have two qubits, they can represent four states, 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time. With just 3 qubits, you get 8 states. With 300 qubits, you could represent more states than there are atoms in the entire known universe. This is the incredible scaling that makes quantum computers a game changer. They don't just get a little faster, they access a computational space that is unimaginably vast, far beyond the reach of any classical supercomputer we could ever build. This ability to hold so much information in a fragile, mixed state is what makes quantum computing so challenging, but also so rewarding. Scientists and engineers have to build incredibly controlled environments to protect these qubits. They must be shielded from the slightest vibration or change in temperature, which could cause them to collapse out of their superposition, a process called decoherence. It's like trying to keep that magic coin spinning for as long as possible. The longer it spins, the more complex the calculation it can perform, pushing the boundaries of what we can explore. As if superposition wasn't strange enough, the quantum realm has another trick up its sleeve. It's a phenomenon so bizarre that Albert Einstein famously called it spooky action at a distance. This phenomenon is called entanglement. Imagine you have two of our magic coins and they are entangled. This means their fates are linked. If you flip them and send one to the other side of the galaxy, the moment you look at your coin and see that it's heads, you instantly know the other coin, light years away, must be tails. It's a perfect, instantaneous connection. This isn't just a theory, it's a proven property of quantum particles. When two qubits are entangled, they behave as a single system no matter how far apart they are. If you measure the state of one qubit and find it to be a 0, you know with absolute certainty that its entangled partner will be a 1. This connection is faster than the speed of light. It doesn't involve sending a signal, the information seems to be shared instantly across any distance. This interconnectedness allows for even more powerful forms of computation and secure communication. In a quantum computer, entanglement links qubits together into a powerful web. A change to one entangled qubit can influence the others in the system. This allows for complex calculations where the information is processed not by individual qubits, but by the collective state of the entire entangled group. It's like having a team of musicians who can all play in perfect harmony without ever seeing a conductor. They are so deeply connected that they act as one. This creates computational shortcuts, allowing quantum algorithms to solve certain problems much faster than their classical counterparts. This spooky connection is the secret ingredient in many quantum algorithms. It creates correlations and relationships between qubits that classical bits could never replicate. Think of it as teamwork on a cosmic scale. While superposition allows a qubit to explore many possibilities on its own, entanglement allows groups of qubits to collaborate on those possibilities in a highly coordinated way. This powerful duo, superposition and entanglement, is what gives quantum computing its almost mythical potential, promising to rewrite the rules of what is computationally possible for humankind. So, we have these amazing qubits capable of superposition and entanglement. How do we use them to build a better future? One of the most exciting applications is in the field of medicine and materials science. Designing a new drug or a new material involves understanding how molecules behave. Molecules are quantum systems. Trying to simulate them on a classical computer is incredibly difficult. But a quantum computer, which operates on the same quantum principles, is perfectly suited for the job. It could design more effective drugs or create revolutionary new materials, like superconductors that work at room temperature. Quantum computers are also poised to solve some of the world's most complex optimization problems. Imagine trying to find the most efficient route for a global shipping network with thousands of ports and vessels. The number of possible combinations is staggering. A quantum computer could analyze all the possibilities at once to find the perfect solution, saving enormous amounts of fuel and time. This same power could be applied to financial modeling, helping us understand complex markets, or to climate change, where we could design more efficient energy grids and discover new catalysts for capturing carbon from the atmosphere. The journey of quantum computing is still in its early days. We are like the pioneers of classical computing in the 1940s, working with large, delicate machines in specialized labs. Building stable, large-scale quantum computers is one of the greatest scientific and engineering challenges of our time. But every day, researchers are making breakthroughs, creating more robust qubits and developing new algorithms. The pace of innovation is accelerating, and the promise of this technology is drawing closer to reality. We are witnessing the dawn of a new computational age. The qubit is more than just a new piece of hardware. It is a new way of seeing the universe. It teaches us that reality, at its most fundamental level, is built on probability and interconnectedness. It invites us to harness the strangeness of the quantum world to solve the biggest challenges facing our own. The cosmos has given us the rules. It's up to us to be curious, to be bold, and to learn how to use them. The quantum revolution has begun, and it promises to reshape our world in ways we are only just beginning to imagine. The adventure is just getting started.